Hello friends, welcome to Joy of Life. So today we are going to talk about binary heaps. So we are going to understand it in all details, understand all the operations that we perform, where we use it and all those things. Start understanding it in more details. So what binary heap is? A binary heap is a binary tree, you can say, with which has the following property. So in a binary tree, what happens is when you first put a node, so at this level, this is level 0. Here it is expected that you will have only one node, so it is. And then on the next level, you have to start filling from the left hand side. You cannot start filling from the right side, right? So on the level 2, again, it will have two nodes. And then if you put a node over here, it's wrong. This is not considered to be a binary heap. A binary heap has to adhere that it has to start filling up from left to right. So it has to come from this. The next node, you cannot put this. This is again wrong because we still have space over here. So this needs to be filled first. So the next node would come over here and the next node should come over here. So the rule is that you fill up from top to bottom, and at each level you should go from left to right. So the tree structure should end up looking something like this, right? And since it's binary, means it will have two child, not more than two childs, right? And the next thing is that you can either create a max heap or a min heap. So how are they different? In a max heap, the root element has to be the highest. So let's say if this is 15, none of these nodes over here can be greater than 15. It can be 15 but should not be greater than 15. So let's say I have a 15 over here and I have a 14 over here. And this subtree now, these node, these can be 15 or lesser, but cannot be greater than 15. So this can be 13, this can be say 9. Over here similarly, this can be 14 and this can be say 12. Similarly, when we create another node over here, it has to be less than 13. So let's say this is 10. So remember, this is also a binary heap, proper binary heap, right? Though there are empty nodes over here, but that's fine. At the last level, all the nodes should be as left as possible. They should not be elsewhere, right? So it is still adhering to the level. And then probably we can have another node over here, 2. So again, 10 and 2 both are less than 13. So we are good. It's still a proper binary heap, right? So where do we need binary heaps and what are the uses of binary heap? This one is a priority queue where we want to set the priority of the element. We can use a binary heap over here, or we can use a heap sort, which is a very efficient sorting algorithm. We are going to see this heap sort in much more details. Then we can use it in several graph algorithms. There are several problems that you can also solve using these approaches, right? Like we have done problem in this channel like kth largest, kth smallest elements and all those things, right? And soon we are going to see how efficiently it does things. Let's understand with some example. Let's take some data and try to analyze them, and let's try to apply binary heap or heap sort on them in order to find out, right? So let's say I have a data like this 1 6 7 4 3 5 2. I have few elements like this, right? And probably you can say that I have received this in an array, right? If you see that we generally do the heap sort, and we never use a tree like structure. We generally use an array in order to solve it. So let's see how a tree can be mapped into an array and how we can do things over here. Okay, so let's say I have this array over here. So let's build the tree out of this first. So how to build a tree out of this array representation? So we will follow the rule that we have learned so far. So one is definitely going to be our root. So we fill from top to bottom and left to right, the same rule we have seen. So we put 1 as the root of the tree, and then we have a 6, so we should do from left to right. So let's put the 6 over here, and left to right, so 7 would be over here, and they are the childs of 1. And then we have 4 3 5 2, so 4 would come and sit over here, 3 would come over here, 5 would be here, and 2 would be here. So we are adhering to the rule. We have created the tree as per our condition, top to bottom and left to right. And now let's see, means how do I know who's 4's parent? Here I can easily look up and say that 6 is my parent. But how do I do the same thing over here? So if I have to manipulate the array and visualize it like a tree, then I have to establish the parent-child relationship somehow, right? So in an array, as you know, that we have the indexes, right? So let's put the indexes of the array over here. So we have these indexes 0 through 6, right? And what we know is we need to identify 3 things over here. So the first one is who's my parent, who's my left child, and who's my right child. So let's say I represent the index over here, right? These are represented by I. So what we can say that we can come up with a formula over here that for parent, what I can say is will be I minus 1 by 2. Okay. So now let's see if it is working or not. So over here, 4, which is at index 3, right? Who's my parent? So 3 minus 1 divided by 2. 3 minus 1 is 2. 2 by 2 is 1. So it says that 4's index is at index 1. So what do we have at index 1? We have a 6. Do we have it matching? Yes, we have it matching. Similarly, for 3 also, for 3, the element 3, the index 4, what we can say? 4 minus 1 by 2. So 3 by 2, we get a 1.5. Cut off this 0.5, what we have is a 1. So 3's parent is at index 1. So we have 6 at index 1, which is correct, right? So for every node it will work. So for if you take 0 for instance, so again you will do what? 0 minus 1 by 2. So minus 1 by 2 will have a negative index. That means it does not have a parent, right? So we know that 1 is the root and it does not have a parent. So we can see that our parent formula is working over here for any nodes. So for left child, similarly, we can say that we will do 2 into I plus 1. And for right child, we'll do 2 into I plus 2. Because we are filling from left to right, right? The next element has to be the right child. So we are doing a plus 2. So let's see if this formula is working for us over here or not. So let's see 7, this node. Who's my right child? 7's right child. So we put the formula 2 into I. This is also 2 plus 2. 2 into 2 is a 4 plus 2, which is a 6. So at index 6, we have 2. And we can see that 7's right child is also 2. Right? Similarly for 1 also, if you see, it is at, so once, let's check out 1's left child, right? So 0 into 2 plus 1. So what do we get? 0 into 2 is a 0 plus 1 is a 1. So 1's left child is at index 1, which is a 6. So yeah, it is a 6, right? So we have established this rule so that our array can work as a tree, right? So that we can manipulate this array, go to the left child, go to the right child and do things, right? This formula that we have came up with is perfectly valid for any tree which is a complete binary tree. So where all the nodes have been filled up from top to bottom, left to right, and all levels are completely filled except possibly the last level, right? Where we have all the nodes, and there also all the nodes should be as left as possible, right? So in those scenarios, this formula will work good. You'll not have any problem with this formula. So with this constraint in hand, let's try to create a heap over here, right? So how this heap creation will work is we will put 1 as the root over here, and whatever changes we do to the tree, so just think that there is no tree in the first place, right? This is just for your visualization, right? And whatever manipulation we'll be doing in this array, and we'll be using this formula in order to look up the left child and the right child, right? So we are doing a max heap over here. We get a 1 and then we put a 6 to its left, right? That's the rule. So as we put a 6 over here, we see that is our condition getting violated. So basically what we do is we go and check that my parent should be equal or greater than me, right? I see no, it is smaller than me. So what I immediately do is I go for a swap. So over here, what happens with this tree in place, 6 and 1 has changed position, right? So we will update them in the array as well. So we are over here, right? Our marker is over here. Then we receive the next element, which is a 7. So our pointer moves on. So it comes over here. So as per the rule, what do? We put the element into our heap. So we put it over here. Again, we check is my parent greater than me. So what we are going to do, we are going to swap these two nodes over here. So our heap is fine, and similarly we should go ahead and update the array. So what we should be doing is we should be swapping between 7 and 6. So the array looks like this, and then we move on to the next element, which is a 4. So we insert the 4 on the left hand side of 1. So what do? I check with my parent. Yes, my parent is smaller than me. So I swap 4 and a 1. And I also swap them over here. Then I move on to my next element, which is a 3. I insert the 3 on the right hand side of 4. We see that the condition is not getting violated. It's completely fine. So there is no operation needed at the moment. So what do? We increment the pointer and we get a 5. So we put the 5 into the right side of 6. And we still see that my parent is smaller. I don't need to perform any operations over here. Then I move on to a 2. So what happens is I know that this is the last element I have to put, and I am done with my first pass over here. So if you look at this array over here, what you will see is that this array is not sorted, right? But we are doing a heap sort over here, right? Though the entire heap is not sorted, but one thing is assured, that we have the highest element in the top, right? So we are going to take this element 7 and swap it with the last element of the heap, which is a 2. So what it means is this 2 over here goes to the top. So this is what happens to our heap at the moment. So why we are doing this? Because we are telling that we are sorting the array with every pass, right? So what happens is I put a marker over here and says that my array is sorted after this marker. So 7 is the only element sitting there, and it is sitting at the right place. So what I'm going to do is I'm going to say 7 is no more in the business. So we are going to disconnect him, and 7 is in its intended place. So what we'll do is we'll put the 7 with a different color. So if you look at it now, that 7 is in its right place, right? So 7 is now disconnected, and we see that rest of the heap is not fine, right? Because 2 is not the maximum element. So what I am going to do is I am going to check both the left and right child of 2, and we are going to pick whoever is greater than 2. So 6 is greater. We are going to take 6 and replace it with 2, and 6 will be coming as the root. So though the array was not sorted, what I knew from this array is that the roots 2 child is either going to be one of the highest element. Now since 2 has come over here, we are going to check is both the child of 2 is lesser than 2. No, it's not. Though 2 has only one child, so we see that child is greater than 2. So we are going to perform a swap. And before that, what we have to do is, since we did a swap with 2 and the 6, so let's update the array. So what will happen is 2 and 6 are swapped. The array is in this condition, and we are performing a swap with 2 and 5. Now we see that 2 doesn't have any more child, and this heap is fine now. This is perfectly a max heap, right? So what we are going to do is we have to update our array, so we have to swap 2 and 5. So if you see over here, 2 was taken to the top and it took only log n, right? So every time, since this is a perfectly balanced binary tree, every time we are discarding half of the tree, right? So we could achieve that operation in log of n time, right? Because every time we are discarding half of the tree, right? So again, once this operation is done, what we are going to do is we are going to do a swap between 6 and 2. So 6 will come over here and 2 will again go to the root. So what we are going to do is we are going to take 6, take 2, and put the 2 over here, and take the 6 over here. But 6, if you see, is no more in gray color, it's in a different color, because we know we are sorted till here. So we are going to remove this line from here. We don't need this anymore, right? So again, what we are going to do, we are going to see who is the greater of the two. So we see that 5 is the greater of the two childs of 2. So we are going to swap 2 with 5. And similarly, we have to update our array. So we are going to get rid of 2 and 5, and we are going to put it back again. So again, we are done with our heap fixation process. We have fixed our heap and it's again a max heap, fine. So what we are going to do is we are going to swap 5 with the last element before the marker, right? So 5 and 3 is going to be swapped this time. So you can see over here how things have started getting sorted from the back side, right? So 3 and 5 we are going to sort, and we are going to disconnect 5 because we are done with 5. So we have 3 and we check, is the root greater than right? Yes, it is. Is the root greater than left? No, it is not. So we are going to do a swap between 4 and 3. And then we are going to update our array as well. So 4 and 3 will be swapped. So again, we see that our heap is completely okay now. So what we are going to do is we are going to swap 4 with the last. So last is at 1. So 4 and 1 is going to be swapped. And of course, we are going to disconnect 4. So the element that does not have the array signifies that they have already been sorted in the heap, right? Though the lines could be there, or because it's an array at the end, you doesn't need lines, right? So what's going to happen is we are going to update this array as well. And also we increment our marker that 132 is not sorted, right? So we are going to check again that who's the bigger of 3 and 2. So we see that 3 is bigger, so we are going to swap with 3, right? And we are all doing this comparisons, finding the left and right based on the relationship that we have established already above, right? So 3 will go over here and 1 will take this place. So we update the array accordingly. So once again our heapify is complete, so we are going to swap it with 2 this time. And just for your visualization purpose, we are going to delink 3, and then we are going to update the array. So 3 and 2 is going to be swapped. So 2 comes over here and 3 goes here in the yellow, right? And we are going to update our pointer to the previous index, right? So now we check 2 and 1 is fine. So what we are going to do is we are going to take 2 and put it here, put 1 as the root, right? And we are going to delink this, right? And over here we are going to put 2 with the yellow, and we have the 1, and then once again we try to heapify and we see that okay, 1 is the last element, so we just increment the pointer and put 1 with yellow, right? So the pointer has traversed all its length now, so there is no need for him to go anymore. So if you see here now that we have our sorting done over here, and you can see here that we have for each element we did a log n pass right over here. So basically if you look at it, what we did a log n for each element on the present in the array, right? So that's why we get a n log n. So for n elements, we did log n time work, right? And this is going to be my complexity over here, the order of n log n. But the best part is that we had a order of 1 space complexity, right? Because we did not use any extra space. So we use the array that's been given to us, and we have established this relationship in order to identify who's my parent and who's my child to get this work done, right? So this is how a heap works basically. So if you wanted to do a reverse of this, then the easiest thing is, instead of using a max heap that we have used, you use a min heap. So what will happen, the minimum element will pop up on the top every time, and you take the element and you just dump it at the back, right? But the best part is, when you wanted to move an element down, every time you will check only half the tree, because since it is a perfectly balanced binary tree, what will happen is it's not skewed, it cannot be skewed, it has to be balanced, right? We cannot create a heap that looks like this, right? It's not possible, right? Because we have to fill from top to bottom and left to right. This will ensure that we are always having a perfectly balanced tree, that both the left and right side, when we eliminate, it will eliminate half of the tree at every pass, right? So yeah, this is the heap sort all about. So I just wanted to give you an overview of what heap is and how heap sort works. So do let me know what do you think about this video. Do comment and do share it also if you think this video was helpful and simple. So yeah, that's all from this video. I'll keep this short. I hope this was a good explanation and you got some clarity based on the discussions that we had on the heap. So yeah, that's all from this video. Do stay safe, do take care of yourself, don't go out, take proper precautions, and yeah, that's all. See you guys soon. Bye bye and thank you.